you're all up for a talk about Henderson-Hasselbalch. This cool equation gives us a way to go between pH and pKa. So let's talk about this equation and how we derive it and what we can do with it.
So I know this probably sounds really boring and it looks really boring, but it's actually really important because this equation is going to allow us to go back and forth comparing the pH, which is a measure of the free proton availability, and the pKa, which is going to be a measure of the acid strength. The Henderson-Hasselbalch equation is going to let us answer questions such as, at a given pH, what is the proportion of acids and base? And it's going to allow us to, if we know the concentration, we can then also multiply this by the proportion by the concentration to get the actual concentration of each. It's also going to allow us to kind of go the other direction. So if we say we know the pKa and we know the proportion of acid and base, what is going to be the pH? And so we can answer all these questions just by rearranging the formula. So let's talk about where this formula actually comes from in the beginning. To start, let's think about what we have in the case of a weak acid. What we have is going to be an equilibrium between the acid and its conjugate base. So let's just talk about how we can talk about this notation. So what we do is we refer to a generic acid we just abbreviate as HA. This is going to be our generic acid. And if this acid gives up a proton, well, now it's going to be its conjugate base. And we refer to this as A minus. And so this A minus is going to be our conjugate base of that acid. And of course, when we have the given up proton, we also have that proton. And so what we end up with is if we have the situation where we have our acid and it can give up the proton and become its conjugate base. And you're also going to have a proton generated. Now, this is a reversible reaction. So it's also going to go the other direction. So what we get is this equilibrium between our conjugate acid and our conjugate base. And remember that each time you generate one of those conjugate bases, you're also generating a proton. Now, we're going to make a simplification, but just so that you know, what's happening is that what's going on is actually happening in a solution of water. So in reality, what we have is we have HA plus water, and this is going back and forth with our conjugate base, A minus, plus H₃O plus. This is what we call a hydronium ion. So what's going to happen is those protons aren't just going to be freely floating around. They're going to actually latch on to one of those water molecules, giving you this hydronium ion. And so this is going to be what you're going to see. However, we are going to kind of ignore water completely. We're just going to say, okay, water, you don't exist. So we're just going to ignore the water. What we're going to do is basically we still want to think about the H plus, but we're going to ignore the actual water part of it. And why can we do this? We can do this because we can basically take water as constant. And why we can do this is because there's so much water compared to our other components. So the molarity of water is actually about 55 molar, which is crazy, crazy, crazy high. So the concentration of our acid and our base is going to be much, much lower. And so basically any small change in the water is going to be negligible. And so we're just going to ignore that. And we're going to focus on just the conjugate acid and the conjugate base. And we're just going to talk about this proton rather than thinking about the proton in the context of actually being in the context of water, in which case you would have to consider like the ionization of water and all of these things. And so we're not going to talk about that. The only place that will come in is when we're talking about like actually the pH, but that's all going to be behind the scenes happening. Okay, so now let's go and let's talk about how we can actually get between the pH and the pKa, and where this equation actually comes from. So what is our goal? Our goal is to get to this equation, and we want to get to this equation by starting with just this equilibrium between our conjugate acid and our conjugate base. So what we can do is we can just kind of write this in different words. So we have that equilibrium, and when we have an equilibrium like that, no matter what type of equilibrium we have, we can write an equation called an equilibrium constant, or we can write a constant called an equilibrium constant. And this is going to be abbreviated KEQ. In this specific case, when we're talking about the acid equilibration, we're going to call this a Ka. And so our Ka is going to be our acid equilibration constant, more commonly called like the acid dissociation constant, or the acid ionization constant. So all of these are talking about the same term. And so what is this term? This term is basically saying that Ka, what we're talking about is we're talking about the concentration of each of our products. So remember that our products are going to be our A minus, our conjugate base, and our proton divided by the reactants. And so that would be our acid. And so this is going to be the Ka. And this is now, we need to relate this ultimately to the pKa and to the pH. So basically what we have to do to get from Ka to pKa, what this P tells you is that this P basically just tells you that what we're talking about is going to be the negative log or the inverse log. So this is going to be inverse log. So that's going to be the negative log, and we're going to be talking about a log 10. So what we're going to have when we talk about this equation is we're actually going to get from the Ka to the pKa by taking the inverse log. And so when we take the inverse log, in this case, we're talking log 10. So we have the pKa is going to be the log of 1 over the Ka, or it's also going to be able to talk about it as negative log Ka. Now, this is analogous to how we get the pH. So this is the same way that this same thing, the same reason we have a P in front of this H in the pH is because, well, that just means a negative log of the proton concentration. So a pH is going to be the log of 1 over the free proton concentration, or negative log of the proton concentration. We can write it either way. So the reason why we take the pKa of this is because now we're going to be able to talk about it in terms in the same kind of scale, in the same sort of terms as we're talking about the pH. So now let's think about what's going to happen if we have a stronger acid or a stronger base. In the equation Ka, we basically are going to have our free, the dissociation, the stronger the dissociation, the more the protons you'd have. And so a stronger acid would have a higher Ka. But it's going to have a lower pKa. Because remember that the pKa, that was going to be our inverse log, because the pKa is the log of 1 over the Ka. And so if your Ka is getting bigger, then that is going to get smaller. And this is similar to how, if you have a higher proton concentration, it's going to lead to a lower pH. So it's the exact same thing with the pKa. So what this is going to mean is that the stronger the acid is, the lower the pKa. And the pKa is going to be the concentration at which half of it is protonated and half of it is deprotonated. And so it makes sense that if you have a stronger acid, it's going to have a lower pKa, meaning that even at lower pH, where there's still plenty of protons around, it's still likely to be deprotonated. So that is kind of like a little bit of intuition about this pKa value. And now let's talk about how we're going to relate it to the pH using the Henderson-Hasselbalch equation. We'll start by taking this form of the Ka, and what we're going to do is we're just going to rearrange it, and we're going to solve for the protons, so we can introduce the pH term, because remember that the pH is going to be the inverse log of the proton concentration. And so we want to isolate this, and then we're going to convert it into the P form. But first, let's just rearrange this equation. And so what we can do is we can basically, we need to multiply both sides by HA over A minus, the concentration of HA over the concentration of A minus, in order to cancel out these terms. So we can say Ka times HA over A minus equals HA over A minus, and I'm talking concentrations here in each of these cases. Do this. Okay, so we can see that these terms are going to cancel out, and what this is going to leave us with is Ka times the HA concentration over the A minus concentration is going to equal our H plus. And this H plus is what we were wanting to find. So we'll just rearrange this and put it on the left, because that's going to be just more conventional. And now we have the Ka, HA, A minus. Okay, this is all great, except that we want pH. So we want to convert this to pH, and we can't just convert the one side of things. Instead, we're going to have to convert both sides to keep things even. So what we're going to do is we're going to take the negative log 10 of both sides. So we're going to get that we're going to have the log of 1 over H plus equals the log of 1 over Ka plus the log of 1 over HA over A minus. Okay, so that's a little unwieldy. So basically I split this up. You can just think about this when you're talking about you can separate this. So what we're going to do is we're going to take the negative log of our proton concentration is going to equal the negative log of our Ka minus the log of our HA over A minus. So when we're doing this like minus log math, we can basically just break things up like this and take the log of this minus the log of this. That's the same as saying taking the log of this whole thing. So we can write it like this. And we want to do this because now we can recognize that this minus log Ka, well, this is what we were talking about as being the pKa. And what about this term, the minus log 10? Hey, that's just pH. So now we're just going to rearrange things yet again. So we're going to move things. Still trying to figure out all this pencils and stuff like this. Okay, but what we can do is go ahead and we'll move this. And now we'll simplify our equations using pH and pKh instead of using the or pH and pKa instead of using these more awkward terms. So we have the pH is going to equal our pKa, and this is going to be minus the log of our acid over our conjugate base. Okay, so we're almost to this equation. Now what we just need to do is we just need to flip this. And when we flip a log, basically what we're going to do is we're going to have to switch this sign too. So we're going to switch sign because we're going to flip this. And this is just one of those logarithm math types of things, where if we want to go from a negative log to a positive log, basically we're flipping this, and then since we're going negative to positive, we're switching this. And so what this is going to give us is it's going to give us that the pH is going to be equal to the pKa, and now we're going to have plus the log of the free conjugate base over the conjugate acid. And voila, that is the equation that we've been trying to find this entire time, is this equation. And so this is going to be the Henderson-Hasselbalch equation. Now let's try to think a little intuitively about this equation. What would happen if you had equal amounts of your acid and your base? So if your concentration of the base equals your conjugation of the acid, what would happen? Well, then you would have log of 1, and that's going to be equal to 0. And so if you have that, well, then pH equals pKa. And this is why the pKa equals the pH at which half is protonated. So that's how we can see where that actually comes from. So now let's see what would happen if we had uneven amounts of our acid and our base. So if we have more of the conjugate base than the conjugate acid, now what's going to happen is this number, this term is going to be bigger. That's going to be bigger. And if you're taking the log of a bigger number, you're going to get a bigger number, and this is going to be a positive number. And so this is going to mean that your pH is going to increase. So if you add a base, your pH increases, which makes sense because in a higher pH, we call that more basic, more alkaline. What happens if our concentration of our base is less than the concentration of our acid? Well, in this case, intuitively, we'd expect that the pH would drop, right? Because that's what we know about pH, is that the more protons you have in there, the lower the pH is going to be. And so if we have more of our acid, we should get a lower pH. And in fact, this number is going to get smaller. And when this number gets smaller, when the thing on the bottom is bigger than the thing on the top, what you're actually going to do is this term is going to get negative. That term's going to get negative. And so we're actually going to go to a pH that is going to be lower. And so if we add an acid, we're going to decrease the pH. So if A minus equals H plus, then we have the pH equals the pKa. So that's kind of like our baseline. And then if we were to add more base, we would increase the pH. And if we were to add more acid, we would decrease the pH. And we can figure out how much the pH will change by knowing the pKa as well as the proportions of the acid and the base that are in there to begin with. If we have roughly even amounts of the acid and the base, well, now if we add a little base, the acid can sop it up. And if we add a little acid, the base can sop it up. And so this is why we get a good buffering capacity around the pKa. It's because we have roughly even amounts of these. So we can see that if we have roughly even amounts, we can calculate that if we were to add a little acid or add a little base, we wouldn't get too far out of whack. But if this is very uneven, we're quickly going to deplete the acid if we add a little base, and we're quickly going to deplete the base if we add a little acid. And so we're not going to have good buffering outside of the range. So we typically think about the buffering range is about 1 pH unit plus or above the pKa. And remember, for each pH unit above or below, you're talking about a 10-fold change. So at 1 pH unit away from the pKa, you have 10-fold more of one than the other, but you still have a significant amount of those, but of each. But if you start showing too far away, then you're not going to have enough. And so we often see this Henderson-Hasselbalch equation being used to try to figure out how much of each of the acid and the base we'll use to make a certain buffer, as well as to kind of see, okay, well, how would this pH change very much in this buffered condition? And so those are the sorts of equations that you're often going to be having to do in your biochemistry course. So this form as is written is really great for if we want to calculate the pH. If we're given the amount of acid and base we have, as well as the pKa, we can then go ahead and solve for the pH. Conversely, sometimes we want to solve for the amount of the acid or the amount of the base. And so what we can do is we can rearrange things to solve so that we're solving for this term. And all we have to do is rearrange things. So we can talk about, we have this log of A minus over HA equals our pH minus our pKa. So why this is useful is if, say, we're at a given pH and we know the pKa, are we going to have more acid or base in that form? So how much of it's going to be protonated? How much of it's going to be deprotonated? That's going to depend on the pKa and how far away from it you are with the actual pH. And so what we can do is we want to undo using the antilog, which sounds really scary, but basically the antilog of 10 antilog 10 is going to be 10 to the x. And we have to do this to both sides to keep things even. So what we're going to end up with is that our ratio of the conjugate base over the conjugate acid is going to be equal to the antilog of pH minus pKa. If we're talking about how at a given pH, what would the proportion of the acid and the base be? Well, here now what we're going to do is we're going to be in the rearranged form, where we're thinking in terms of the pH minus the pKa. And the value that we're trying to solve is going to be this proportion of the acid to your base. So we can write things as the log of A minus or HA equals the pH minus pKa. And this is going to be some value that will be given. We'll know the pH or we'll know the pKa, and so we can just subtract those. Now to undo this, we'll take the antilog of both sides. And so we'll get A minus over HA is going to be equal to the antilog of our pH minus pKa. Remember, antilog sounds scary, but really we're just saying 10 to the x. So this would be 10 to the pH minus pKa. If we have 10 to the 0, so if our pH equals pKa, well, then this is just going to equal 1, which is telling us that this ratio is going to be equal to 1, which makes sense what we talked about, that the pH is equal to the pKa when you have equal amounts of your acid and your base. If you have 10 to the 1, that's going to be equal to 10. You'll have 10-fold more of your conjugate base if you're one pH unit above the pKa. And if you had 10 to the -1, that's going to be 1/10. So you'd have 10 times more of the acid form. And so you can do this. It's easiest to think about this in terms of these nice round values, but you can also do it with any number. And so in each of these equations, what you're solving for is you're solving for this proportion of the acid and the base. If you know the actual molar concentration, you can calculate the exact concentrations of these. But right now, we're just looking at the ratio of them. So typically what you're going to be given is you'll have some situation where you'll say like, okay, the pH is 7 and the pKa is 6. What is the concentration? What proportion of this is going to be protonated? What proportion is going to be deprotonated? And so in that case, you would say, okay, well, my pH is 7, my pKa is 6. 7 minus 6 equals 1. And so I would have this 1. And then I would take 10 to the 1, and that would give me 10. And so that would tell me that 10-fold more is going to be deprotonated than is protonated. Now, similarly, what would happen if our pKa was 1 above the pH? So if we had our pH of 7 and our pKa of 8, well, now if we have 7 minus 8, we get -1, and the antilog of -1 is 1/10. And so if we go one below the pKa, we're going to have 10-fold more of the acid form than the base form. And we can, so for every, this is a fundamental thing, for every 1 pH unit away from the from pKa, you get 10-fold change in protonation. So a little, like a 1 pH difference might not sound like that much, but it actually is a lot. And so if you go 1 pH unit below the pKa, well, now you have more protons available. You're going to have 10-fold more protonated. And if you go above the pKa, you have fewer protons available. You're going to have 10 times less protonated. And much more on some sort of intuition about that sort of thing in other posts. But today, I just wanted to tell you where this Henderson-Hasselbalch equation comes from. So to review, we took it by taking the equilibrium constant of the acid, which we just do by the products over the reactants. So the concentration, so the products over the concentration of the reactants. And so in this case, when we have this, the weak acid, we're talking about this HA is in equilibrium with the conjugate base and the proton concentration. And so these would be our products. This would be our reactant. And we can write this equilibrium constant that we call Ka. We want to talk about this in terms of the proton concentration so that we can compare it to the pH, which is a measure of the free proton concentration. And so what we did was we isolated this equation to solve for the proton concentration. This allowed us to isolate this proton concentration, but now in order to talk about it in terms of pH, we actually needed to take the inverse log of things so that we got it on the pH scale and not just the H+ scale. Because the pH is the inverse log of the proton concentration, not just the proton concentration, so we need to find the inverse log of it, which means that we also are going to need to find the inverse log of our Ka. And so this is how we ended up with the pKa. We took that inverse log of the Ka, we took the inverse log of the H+, and then we could substitute in pH once we had done that. Then it was just a little bit of rearranging things and canceling out the sides of the equation, making things more convenient. And then ultimately we ended up with this equation that then we could rearrange depending on what information that we started with. This leads to some fundamental concepts, including the idea that when the pH equals the pKa, you have equal numbers of your protons and of your conjugate acid and your conjugate base. And that's going to give you a pH that equals the pKa. If you go 1 pH unit above the pKa, you're going to have 10-fold fewer protons. You're going to have 10 times more in this deprotonated state. If you go 1 pKa unit below the pH, 1 pH unit below the pKa, you're going to have 10 times more of this HA. And this is all because we're talking about a log 10 scale. And so basically remember that log 10, each change of 1 is like a 10-fold change. And so this is why we get a change of 10. And this is all encompassed in this key equation, the Henderson-Hasselbalch equation. So I hope that helps you appreciate it. And if you ever forget it, you can hopefully derive it for yourself, as well as I encourage you to just derive it as a way of kind of like studying and thinking through some of these things. Apologies for the messy handwriting. I'm still trying to figure this out, as well as kind of like the best note-taking softwares and things like this. But hopefully these sorts of things will get better as I get more into teaching. So hope this helped.